Okay, so when you compress the spring, when is the mass attached to the spring going the fastest? I'm sorry? I've compressed the spring. Here's the equilibrium position. I'll let go. When is it going the fastest? At equilibrium. Okay. So similarly, we've compressed this plunger. We compressed it 0.15 meters. That's 15 centimeters. Okay. And you fire it, and it will be going the fastest at equilibrium when the spring is uncompressed. Okay. And so this is 0.15 meters, and the mass of the plunger is 0.05 kg. That's 50 grams, and it's going at 20 meters per second. Okay, so what is conserved here? What is happening? Remember, the total energy is conserved. Here, it's all potential energy. You compressed it, it's at rest. And here, it's all kinetic energy. Okay? So the total energy is 1/2 Ka square, and that should equal, which is what it has here, and that should equal the kinetic energy at this point, 1/2 mv squared. So K is equal to mv squared over A squared. M is the mass of the plunger, which is 0.05 kgs. V is 20 meters per second. And amplitude is 0.15 meters. And this is the spring constant, and that'll work out in Newton per meter. So. Okay, so your weight is this is about 20% greater than your weight. So 1.2 of you have to hang on to the spring to stretch the spring by 1 meter. That's what that means. So that tells you the strength of the spring. So if I hang on to the spring, it'll stretch by 1 meter. Yep. Okay, uniform circular motion, is it related to a mass attached to a spring? Okay, how is it related? Two simple harmonic oscillators, okay? So, you can use a saw and make it move like a mass attached to a spring, and that'll work, right? That'll cut through stuff. So here is the idea. This is called a reciprocating saw. What you do is, an electric motor, it's easy to make something spin. So you take an electric motor and make this thing swing, and you can attach with a rod, you can attach a saw. And as this thing rotates, that makes the saw go back and forth. Okay. So that's a practical way of doing it. You can't make an electric motor go back and forth. This is how you can do it. So if the motor rotates at 60 hertz, that is, it's going through 60 revolutions per second, and has a radius of 3 meters, estimate the maximum speed of the saw. Okay, the maximum speed of the saw, you can check on your, so V max for an oscillator's A times omega, the amplitude of oscillation times omega. So the radius of this wheel is the amplitude of oscillation. Okay, so this thing goes back and forth 6 centimeters, and the saw goes back and forth 6 centimeters, and its amplitude is 3 centimeters. Okay. And omega is the angular speed, which is 2 pi f. Okay, so A times 2 pi f. So 3 centimeters, 2 pi, 60 hertz. Hertz is 1/2. So the maximum speed of the saw, and that happens when it's at the center, is that many meters per second. So this is 180. So the maximum speed of the saw is 11.3 meters per second, I guess. And it's happening at the middle of the oscillation. And 11.3 meters per second, Usain Bolt can't run that fast. He runs about 10 meters per second. And that's about 25 miles an hour. How long does it take a child on a swing to complete one swing if her center of gravity is 4 meters below the pivot? Okay, so this is the length of the pendulum, and this is one oscillation. And the period is given by 2 pi L by G. If you look at some of the old Apollo movies, when we landed on the moon, one of the first things Armstrong did was there was a pendulum hanging on the lunar lander, and he set that in motion. And the reason he did that was kids watching on TV, they were told the length of the pendulum. They could measure the period using their stopwatch. Okay, so you measure the time for 10 oscillations and then divide that time by 10. So you can measure the period. They were told the length of the pendulum, and so they could calculate the acceleration due to gravity on the moon. So sitting in your living room, you could get the acceleration due to the moon. So they're asking you to calculate the period, 2 pi over 4 meters divided by 9.8 meters per second squared. So the period is 4 seconds. Mm-hmm.
That equation is that only for a pendulum motion?
That's for a simple pendulum. Yep. So there's the center of gravity of the child, and that's 4 meters below. So that's the length of the pendulum effectively is from the pivot point to the center of gravity of them. So a simple pendulum is a small, heavy object. Small meaning small compared to the length of the string. What is the effect on the period of a pendulum if you double its length? So if you double its length, the period increases by √2. So the period is given by 2 pi or L divided by G. So if you double its length, the period will increase by a factor of 2 pi. What is the effect on the period of the pendulum if you decrease its length by 0.5? If you by 5%, then that would go to 0.95 length, and the period would change by square root of 0.95. Okay. Okay. If a car has a suspension system with a force constant of 5 times 10 to the 4 Newton per meter. Okay, so this is the suspension system in your car. That's 50,000 newtons. So you would have to have 100 people sit on the car for the suspension system to compress by 1 meter. That's what that means. So it's a very strong spring. How much energy must the car's shock remove to dampen an oscillation starting with a maximum displacement of okay, so how much energy must the car's shocks remove to dampen the oscillation starting? So the oscillation is 0.75 meters, okay? So the initial energy is 1/2 Ka squared. And so you're trying to kill that oscillation, so you have to remove that much energy. That's how much energy there is when the oscillation starts. 1/2 K is 5 into 10 to the 4. And the amplitude is 0.075 meters. Hundred and 40 joules of energy. And so the oscillation is 3 inches of oscillation. So the car is oscillating like that, 3 inches. That's the amplitude of oscillation. And you have to kill those oscillations and 140 joules. So here's how you mgh, let's say my mass is 60 kgs, so I guess we'll say 65 kgs or whatever. 65 times 10, that's 650, and 650, so times 0.1 is 65, times 0.2. So if I jump this high, that's the energy I have, 20 centimeters. Okay. Suppose a diving board with no one on it bounces up and down in simple harmonic motion with a frequency of 4 hertz. The board has an effective mass of 10 kg. What is this simple harmonic motion of a 75 kg diver on the board? So the frequency is given by 1 over 2 pi k over m. Okay, so as you increase the mass, effective mass, the frequency decreases. Okay, when the mass is 10 kgs, the frequency is 4 hertz. And then somebody gets on the board, so you're increasing the mass from 10 kg to 85 kgs, effectively. Okay? Greater the mass, lower will be the frequency. Okay? So F1 will be equal to F0. So initial frequency was, okay, well, actually. Initial mass was 10 kgs, and now with somebody on, it's 85 kgs. Okay, so the new frequency is 1/3 of that. Okay, this says a suspension bridge oscillates with an effective force constant of 10 to the 8 Newton per meter. How much energy is needed to make it oscillate with an amplitude of 0.1 meter? So this calculation, so in the bridge, so for instance, the wind was pushing the bridge, you have an effective constant of the bridge, and 0.1 meter, that's the oscillation, 10 centimeters. That's the amplitude of oscillation. So for the bridge to oscillate like that, how much energy did the wind pump into the bridge? Okay. So 1/2 Ka square and this is 10 to the minus 2, so this makes it 0.5 times 10 to the 6 joules. Okay, so have you guys heard that when a battalion marches across a bridge, they break up the battalion. They don't let you march across the bridge. Why? Because if your frequency matches one of the natural frequency of the bridge, you can break the bridge by the time you get across. Okay. So if soldiers march across the bridge with a cadence equal to the bridge's natural frequency, that is, you're forcing at a frequency matching the natural frequency, and impart 10 to the power of 4 joules of energy each second. So each time, every second you're pumping in that much energy. Okay. How long does it take for the bridge's oscillation to go from 0.1 meter to 0.5 meters? So how long does it take to make the bridge oscillate from there to there? Okay. All right, so the increase in energy is 1/2 Ka2 square minus. Okay, we've already calculated the energy for there. Now let's calculate the energy for this amplitude. One half 10 to the power 8 Newton per meter, 0.5 meters squared. All right, so the increase in energy, so the initial energy was 500,000 joules, now 12.5 million joules, so the increase in energy is 12 million joules. All right, so each second they're pumping in 10 to the power 4 joules. Okay. So the time is 12 million joules divided by 10 to the power of 4 joules per second. So 1200 seconds, 20 minutes. So if the battalion marches, it takes them 20 minutes to march across. You can potentially, the oscillations went from here to there, and that could break the bridge.